So an IP address is a 32-bit number identifier for a host or the router interface, right? So every router interface here, every router interface has an IP address, and also each host interface needs to have an IP address. So a host can also have more than one interfaces, and in this case, every interface needs to have an IP address, right? It's a 32-bit number. Usually a dotted is represented a dotted decimal number. For example, 223.1.1.1, or I can write it, an example, or say 176. You must be familiar with this 172.16.17.1. So we call it a dotted decimal number. That is for our own convenience, obviously, because when a router or a machine has to perform some sort of operation, so it has to convert this dotted decimal number into binary equivalent. Okay, so so we can clearly see that this 32-bit number has 4 octets. This is 1 octet, 8 bits, another octet, third octet, and we have 4 octets. So it has 4 octets, and each octet represents a decimal number for our convenience. Before I go into the detail and talk about 32-bit binary IP address, let me quickly talk about the type of addressing that is available to us. There are 2 types of addressing, IP addressing, that we will be discussing that is available to us. Number 1, there are 2 types of IP addressing. Number 1, we have classful addressing. Classful addressing, or addresses. And then we have the second type is classless. We call it classless inter-domain routing. Okay, let me first quickly talk about this classful addressing and classless addressing. So in classful addressing, the number of bits that are representing the network part are fixed, right? So we have divided in classful addressing the IP addresses into different classes. For example, we have class A, class B, and then we have class C, class D, class E. So what we have done is we have divided IP addresses into 5 different classes, and in each of the class, the network prefix is fixed. For example, the bits that are representing the network part are fixed. For example, if an IP address is 12.12.34.158.0, and I have this prefix 24, this means 24 bits are representing the network portion, right? And similarly, if I'm using this address, for example, 10.0.0.0, there the 8 bits are representing the network part. This means this belongs to class A. I'll be discussing these classes in detail in a minute, right? So we have divided the IP addresses into classes, right? But the problem with classful addressing or addresses is, so what are the problems here? By the way, this class A has a very large block. There are 24 bits for the host portion, And then we have class B. Class A is class A is very large. Then we have class B, which is large. Class C is small. Class D is class D is basically for used for multicasting, right? And class E is reserved for future use. Class is very large. Class B is large because it gives me enough number of hosts in class B. We'll see in a minute how. And then class C is small, right? It gives me less number of machines per IP address. The problem with the problems with classful addressing is that number one, that it's the Goldilocks problem. I hope you understand this Goldilocks problem. You must have read the story of a Goldilocks and three peers, right? So where everybody wanted a class B. So everybody wanted a class B because class B is large and class B is small and class A is very large. So class B is sort of the best fit, the ideal, right? And this fixed distribution of network and host addresses may result, and in fact, it results in, it results in inefficient use of the address space. So this means the address space usage became inefficient. Right, and it's also possible that the address space become scarce. Because of this inefficient use of address space, the address space became right. So, for example, they predicted that by 1992, the class B has been, half of the class B has been allocated and so on and so forth, right? So the other possibility is that we have IP addresses where there is no fixed distribution of the bits representing either the network part or the host portion, right? So the network part, so the basic of this classless interdomain routing or classless addressing is that the network portion of the address is of arbitrary length and is determined by the prefix mask. So the network portion of address is of arbitrary and then the question arises how we will identify that how many number of bits are representing the network portion. So it is determined by a prefix. Okay, for example, I can have this address 200.23.16.0 and this prefix 23 is identifying that how many number of bits are representing the network part. Yes, you're right, 23 bits, right? So so let me talk to you, let me have this basic discussion about an IP address to make these two types of possibilities of IP addressing more easy to understand. So an IP address is represented by a 32-bit binary number, and it has 4 octets. And as we move towards the left in an octet, the value of the octet is doubled, right? And for our convenience, we represent it as dot decimal number, and an IP address. So let's try to understand with the help of this example here. So there are how many number of octets? Since there are 32, there are 32 bits here. So 1, 2, 3, 4 octet. And octet means how many number of bits are there? Obviously, we have 8 bits. And as I move towards the left in an octet, its value is double. The value of the first bit is 2 raised to power 0, which is what? 1. The value of the second bit is 2 raised to power 1, 2. The value of the third bit is 2 raised to power 2, 4. The value of the next bit is 2 raised to power 3, 8. Similarly, 16, 32, 64, and 2 raised to power 7, 28. Right? So as I'm moving, you can see, as I'm moving towards the left, in any of these 4 octets, the value of the bit is doubled. 1, doubled, 2, doubled, 4, 8, 16, 32, 64, 124. And if all these bits are 1, in any of the octets, this means what? This means I will add all of these values, and the maximum value of this octet would be 255. So the maximum decimal value of each octet is 255, and this is the case where all these bits are 1, right? Means their value is set, right? So we can easily determine the value of any of these octets. For example, what is the value of this octet at the moment? What this binary number is representing here? So we have this 128 bit is on and 64 bit is on. So what is the value of this octet then? Yes, you're right. 128 plus 64. This is 192 dot. What do you think? What is the value of this octet? 2 raised to power 0, 1. 2 raised to power 3. Sorry, 2 raised to power 2, 4. Yes. So all other bits are 0. 192.5. And what about this octet? 2 raised to power 1, which is 2, and 2 raised to power 5, which is 32. So 192.5 dot, yes, you're right, 34 dot, 2 raised to power 1, 0 is on. This means 2 raised to power 0 is 1, 2 raised to power 1 is on, which is 2, 2 raised to power 3 is on, which is 8. So the value of this octet is 11. So this binary representation of these 4 bits are represented in the IP address 192.15.34.11. Right. So this is how we can represent our dotted decimal number into binary equivalent. And if we're given this binary equivalent, we can easily represent it with the help of dotted decimal number. So an IP address has 2 portions. An IP address has a network portion and a host portion. So the network portion of an IP address identifies the network that a host belongs to, right? So this will take me, or this will help the router to forward the packet to the specific network. And this host identifies the specific host in that network. Now the next question is, how many bits or how many number of octets are representing the network part, and how many octets are representing the host portion? And the answer depends upon that either I'm talking about classful addressing or I'm talking about classless addressing, right? So if I'm talking about the classful addressing, so different classes specify that how many number of bits or the octets would be representing the network portion and the host portion. By the way, since IP address is a hierarchical address, this means this network address will help me to reach or to make the routing decision to reach a specific machine network first, and then the machine inside the network. So let's assume that we are talking about the classful addressing, and as I have discussed earlier, there are total how many number of classes? There are total, yes, you're right, there are total 5 classes. So we have a class A, we have a class B, and then we have a class C, and we also have a class D here that we use for multicast group. And then we also have class E. So we also have class D. There is also class E, and this is reserved for future use. Okay, so how many number of so in total we have 4 octets. So what do you think? How many number of bits or how many octets are representing class A? Yes, so we can clearly see that with the help of this diagram, that in class A, the first octet, the leftmost octet, represents the network portion, and the remaining 3 octets represents the host portion. And in class B, first 2 octets represents the network portion, and remaining octets represents the host portion. And in class C, first 3 octets represents the network portion, and the remaining octet represents the host portion. Let's try to discuss this in detail, and let's talk about the first class, class A. In class A, as we have discussed in the previous slide, that the first octet, the leftmost octet, the most significant 8 bits represent the network portion, and the remaining 24 bits are for the host portion, right? And remember that the leftmost bit of the leftmost octet will always be 0. So this means what is the value of this bit, by the way? Yes, you're right. This is 2 raised to power 7. And what is the value of 2 raised to power 7? 128. So this means I will never on 128. So this gives me the range of IP addresses in class A. And this range is between 0 to 127, but 127 is reserved for a special purpose that I'll discuss in a minute. By the way, it is used for localhost. So we do not use this 127. So this means anything between 0 to 126 is representing class A address. For example, if this address is given 12.95.64.15, so this address belongs to, yes, this is a class, this is an IP address of class A. Why? Because I will just look at the first octet and we'll see if the value of the first octet is between 0 and 126. This means this address belongs to class A, right? So obviously its value is between 0 and 126. So this address belongs to class A, right? Similarly, the address given here in this example, 124.95.44.15 is also class A IP address. Why? Because 124 is between 0 and 126. So the range is effective range is between 0 to 127. 127 is not used, reserved for localhost. So that's why the range is from 0 to 126. Why its range is from 0 to 127 or 6? Because we never on this the leftmost bit of the leftmost octet means 128 is never on, right? So this means the remaining 24 bits are for the host portion. So how many number of IP addresses we can have against one class A IP address? So how many number of host addresses we can have against one class A IP address? That is 2 raised to power the number of bits in the host portion, 24 minus 2. This comes out to be, this is about 16.7 million possible IP addresses that can be assigned to machines having one class A IP address. That's why we call it it's a very, very large block, right? For example, MIT has this block where this address is 18.0.0.0, right? Okay. So big ISPs or companies having a very large number of nodes need to have this very large IP address. Okay. And obviously, the first 8 bits will be used to reach the specific network. Why? Because these bits are representing the network portion here. Okay. And if I talk about class B, in class B, the first 2 octets represents the network portion, and the remaining 2 octets represent the host portion. And remember, the leftmost 2 bits of the first octet of these 32 bits is always 1, 0, right? So this means what? That 128 is always on. I will always consider, 128, and 64 is never on, right? So this means the range of, if all the remaining bits are 0 in this octet, the range of class B will start with 128. And if I assume that the other bits of this leftmost octet, leaving this 64, are on, so this means what? We have 32, 16, 8, 4, 2, 1. And if I add 128, 32, 16, 4, 8, 2, 1, this will give me what? Value 191, right? So any address having the first value of the value of the leftmost octet between 128 to 191 belongs to class B. For example, this address here, but just looking at the first octet, I can say this is class B address. Why? Because the 151 is in between 128 and 191. And similarly, the earlier example, 172.16.17.4 also belongs to class B. And how I'm deciding? Just looking at the leftmost octet, the first value, I can identify that it belongs to class A or class B. And then how many number of, since the first 2 octets represents the network part, how many number of bits are there for the host portion? Yes, these remaining 2 octets, right? Okay, 16 bits. So how many number of host addresses I can assign in a network having a class B IP address? Yes, you're right. 2 raised to power the number of host, the number of bits in the host portion, 16 minus 2, because we leave the specific addresses, that network address and broadcast address, that minus 2. This gives me 65,534 addresses. So it's large. It's not very large, but this block is large, and that's why everyone is after class B, right? And that's why we call it a Goldilocks problem, that where everybody wants a class B address. Okay, and now let's talk about class C. In class C, the value of the leftmost 3 bits are always 1, 1, 0. This means what? This means 128 is always on, 64 is always on. We never use 32, right? And if so, this will define the starting range of class C, which is 128 plus 64, right? Which gives 192. And if I assume that all other bits are also set and the leftmost octet are on, so this means I have 16 and 8, 4, 2, 1. If I add 128 plus 64 plus 16 plus 8 plus 4 plus 2 plus 1, this will give me a number 223. So the range, the effective range of class C IP address is between 192 to 223. The IP address of your PTZ router, for example, is 192.168.1.1. So I can quickly identify that just looking at the first decimal value, that this address belongs to class C, because this value is between 192 to 223. right? And by the way, how many number of bits are there in the host portion? Yes. So we have 8 bits. So 2 raised to power 8 minus 2. We have 254 hosts per against each IP address. That's why we call it a small block, right? Where we have fewer number of IP addresses available against each address space. Right. So the next question is how we can get an IP address quickly. So either we can assign an IP address, we can hard code it um, in the properties of in the network configurations, or we can have this dynamic host configuration protocol to dynamically get IP addresses from a server. We also call it plug and play. Please get IP addresses from Internet Corporation for assigned names and numbers. So this corporation is basically responsible for allocating addresses, managing DNS. DNS we have already covered, assigning domain names, and to resolve disputes if there are any, right? So we'll also be talking about, by the way, IP addressing in the next class, where we'll be discussing subnetting in detail. So the next topic of discussion is network address translation. So network address translation is basically a stopgap measure to handle the IP version 4 address exhaustion problem, because the IP version 4 addresses have exhausted. And we have some free series IP addresses in each class that we can make use of without buying it from ISPs. For example, we have 10.0.0.0.0. It's a free series in class A. Then we have 192 dot. Then we have Then we have 172.16.0.0. So this is the free series in class A. This is the free series in class B. And then we have 192.168.1.0 in class C. So these are the free series that can be used by, that can be used by any machine in any network. But the problem is, if I am making use of this free series address, and one of my machine has this address, say 10.0.0.1, so maybe there are hundreds and thousands of machines in the world that may be using this same free series IP address. So if I make a request to Google, so where the response would be, right? Either because there are many machines using the same free series IP address. So this means we can make use of this free series, but we also need to have a way of translating or replacing this free series address with a net IP address, or with a real IP address, with a unique IP address that is not used by any other machine in the world, right? So the NAT, what it does is that it shares a limited number, which is greater than 1, of global static address by a number of local hosts. So for example, this number here is global, and it's static. And this number here I'm sharing with all of my local network machines using free series. Okay, and the local to global address binding is done connection by connection. So if this machine is sending a request to Google, so I'll have this conversion here at the NAT at this router, right? So all the datagrams leaving this local network have same single source NAT IP address, or global or static IP address, which is unique, right? But their port number would be different. We'll see in a minute, right? So all the datagram with the source of the destination network have the usual free series of IP addresses, and we need to see how this conversion is done. So the network address translation. So the motivation is that the local network uses just one IP address as far as the outside world is concerned. So for the outside world, all these machines are being represented by this one global or static IP address, right? We cannot share these addresses. Why? Because these are free series addresses, and many other machines will be using these free series IP addresses. And no need to allocate range of addresses from ISP. Just one IP address is used for all the devices. So why? Because we have already this shortage of IP version 4 addresses. So why should we be assigning the global or the static IP addresses to all these machines? There's no need of it, right? When I can make use of these free series IP addresses, and I can use one global static IP addresses for all these machines. So we can change addresses of the devices. The other advantage of the motivation is that we can change the addresses of the devices in the local network without notifying the outside world. So within the network, I can change an IP address of any local machines, and I do not need to let anybody know about it. And we can also change the ISP without changing the addresses of the devices in the local network. So maybe I can change it to another IP address. I can change this global and static IP address, and I do not need to change the IP addresses of the local machine for that, right? And the devices inside the local net not explicitly addressable. So this is a sort of like security plus. So nobody knows that a device inside, this network has IP address 10.0.0.1 because I'm representing it with a global address, right? So let's talk about the implementation. So a NAT is a box function that replaces the source IP address and port number of every outgoing packet to NAT IP address and new port number, which is generated randomly. We'll see with the help of an example in a minute, right? And remember this, in this NAT translation table, every source IP address and port number is mapped to NAT IP address and a randomly generated port number. So it's a pair. We'll see how it works. I'll leave it with a question mark. So every incoming packet replaces the NAT IP address and new port number in the destination field of every incoming datagram with corresponding source IP address and port number stored in the NAT table. Okay, and let's try to understand this with the help of an example, right? So what we said first. So first, what a NAT router does is that it replaces the host IP address and port number with NAT IP address and with some new port. So let's assume as a first step that a machine having source address 10.0.0.1 using a process ID 3345 wants to connect to a machine having IP address 128.119.40.186 on port 80. This request will first go to the NAT translation table at NAT router. So here it will do the first replacement, where it will replace this part, right? Where it will replace this part with the NAT IP address and with a specific random port number, right? So what happens as as a second step? So we have this entry on the LAN side, which is the connection request coming from a machine having IP address 10.0.0.1 from port number 3345. And now what I've done is that I've replaced this IP address with the NAT IP address, which is 138.76.29.7 and a randomly generated port number, say 5001. Now look at the packet that is being forwarded from the network. Here the source address is the address of this NAT IP address, the global static address. and the request is being generated from port number 5001. And this field is the same. The destination is, you can see the destination address is the same, and the port number is also the same. Right. Now we will receive a reply from the destination 128.119.40.186 from process or port number 80. What will be the address of the destination in response? Okay, let's try to look at it. Now, a response is generated by the destination. Destination is now the source, obviously. So this is the same, right? So you can see that we have the same entry in the source now, because this destination is the source now. It is generating the response. So the source address is 128.119.40.186, and we have port 80. So where it is going? Now the destination address is, yes, static IP address, okay, or net IP, which is 138.76.29.7 at port 5001. So as the net router receives this packet, it immediately looks at the port number 5001, and it looks at the corresponding entry on the LAN side. So what is the entry on the LAN side? Yes, the address of this machine, which is 10.0.0.1, and the process address, which is 3345. So immediately it replaces the destination address with the LAN side entry here, right? So now look at the destination address in the packet that is being forwarded by the NAT router here. So the destination is 10.0.0.1 and the port number is 3345, right? So NAT IP address and the new port in the destination field is replaced with the source IP address and the port number. And this is how the response is forwarded to the specific host in a network, right? Let's try to look at the advantages and disadvantages of NAT in detail. So we want to talk about network address translation advantages and disadvantages. So let's talk about first the advantages. Okay, so the first advantage is that it can change the address of a device in the local network without notifying the outside world, right? So this means I can change the IP addresses of the local machines, and I do not need to tell anybody outside the network. So we can change address of devices in network without notifying outside world. And the second advantage is that the devices inside the local network not explicitly addressable by or visible to the outside world. So you can say it's a security plus, right? So it has a security plus. Why? Because the outside network or the machines cannot address the local machines directly. Then let's talk about the disadvantages. Disadvantages of NAT network address translation. So the first disadvantage is that the devices inside the local network explicitly are not explicitly addressable by or visible to the outside world. It's also a disadvantage, right? So devices inside local network not explicitly. Obviously, we can access it, but not explicitly. Not explicitly addressable. By the outside. Okay. Why it's difficult? Why it's a disadvantage? Because it makes peer-to-peer networking much harder. Okay. So if I cannot address a device directly, the peer-to-peer networking is a difficult task. And the routers should not or should process only up to layer 3, right? Routers should only process up to layer 3. I mean, it should not be dealing with port numbers, because port numbers is something to be, are application layer objects. Okay. And third thing is, why we have to deal with the address shortage with this NAT? Well, instead, NAT is hindering the adoption of IP version 6. So NAT hinders the adoption of IP version 6. So we can easily replace this, shortage of IP addresses by deploying IP version 6. But NAT is, also creating a problem in this case. So NAT is controversial, as we have discussed, that it should only process up to layer 3. But in this case, a router also has to process the port numbers also, and it violates end-to-end argument, because if a local device is not directly addressable by the outside world, this will make the development of peer-to-peer applications difficult. And obviously, as we discussed, that we can obviously address the shortage of address shortage with the help of IP version 6, but this NAT is in fact hindering the implementation of or adoption of IP version 6. So this concludes our today's lecture. So in this lecture, we have talked about IP version 4 datagram. We also talked about the services that are provided by the network layer. Then we talked about the basics of IP version 6 addressing. There are two types of addressing: classful addressing, where we have specific classes, where the number of bits representing the host and the network portions are fixed. And then we talked about the classless interdomain routing, classless addressing, where a prefix identifies where there is not clear fixed division between the network address, the bits representing network part, and the host portion. And to identify the network part, we have this prefix that identifies the number of bits representing the network portion. And then we talked about the network address translation, at how using IP version 4 addresses we can address the shortage of IP version 4 addresses using network address translation. Dear students, thank you. Allah Hafiz.